All right, welcome. So the final part of my little video series on PCB intro design for Dalhousie University here, I'm going to talk about MOSFET selection, and in particular what I want to end up with is talking about how you select the parts in KiCad. If you're using a part that has a model in KiCad, it's kind of easy. You can just use the model, but a lot of the time you won't. These parts change, so there's a little kind of oddity with the naming of the packages and how the pin numbers go and stuff. So if you're just getting started, it can be good to know about that so you don't get confused when you're going to do your design. Before I do that, I'm going to talk about how you select a MOSFET. This is a pretty quick overview, but I feel like if you're just getting started, this also could be useful to know. So a MOSFET is basically an electronic switch. The parts of a MOSFET, so we have like a source, a drain, and a gate terminal. And this is what's called an N-channel MOSFET, which means that as the gate goes more positive than the source, then the MOSFET starts to turn on. And when we look at this, we're going to have a few specs of importance to us. We have some load here that we're driving current through, right? So this is I. The first thing that we're going to see is something called ID, which is the drain current in the MOSFET. So this is the drain current going into the MOSFET. There's a maximum value. If we go over that, it'll burn up. But we're, in this case, we have, say, 5 amps going through at most our load. And if it goes above that, we have a fuse in our system. It's not shown on the schematic, but this is some of the design requirements. So when you look for a MOSFET, you might just say, great, I only need 5 or maybe 10 amps. But in reality, you may end up with like 100 amps or a really high value. And the reason you may end up with a really high value is one of the considerations, not that you have to have such a high value, is that a MOSFET's basically like an electronic switch, but it has some resistance. And this resistance is the resistance between drain and source. So it's RDS, and it's normally called RDSon. So the resistance from drain to source when it's on. And if you think about, the power being dissipated by the MOSFET, power is equal to current times voltage, or voltage times current, but I'll put it this way because what I'm then going to do is replace this voltage with, that's the voltage across the resistor, which is, equal to current times resistance, this RDSon. Which means the power dissipated in the MOSFET is directly related to this RDSon. So what we actually want is the lowest RDSon, or a reasonably low RDSon, that gives us a very low power dissipation for a given current. So what we kind of care about more is looking at, okay, if we're only really passing 1 amp most of the time, then we might be able to accept a pretty high RDSon. Even 5 amps isn't bad. But if you were designing a higher power system, this power dissipation can become very significant. All it means is that you maybe need a heatsink to achieve, if you're passing the full current, you need a bigger heatsink. But if we overspec the MOSFET, then we can get away with absolutely no heatsink. So this is a calculation you can do, right? Don't just arbitrarily decide, oh, Colin said use a really high current, so I'm going to use a really high current. There's a pretty quick calculation. The datasheet's going to also have a spec for how much power gets dissipated and how hot the part gets, which will be based on some rough assumed PCB. But all of this you can kind of do very ballparky type calculations on. The other reason I bring this up and I really highlight this is this also defines how our gate voltage gets driven. So one of the other specs you're going to see is the gate voltage for the RDSon. Normally it gives you the minimum gate voltage you need for maximum RDSon, because as the gate voltage is lower, what happens is, so you might see a few different figures. In this case, we have an ID, a current draw limit. And so it's saying, for a gate voltage of like 3, what's this? This should be like 3.3 volts. You can only put through maybe 1.5 amps. And this also may mean that the RDSon is actually kind of high at this point. If we try to put through that current, it's really heating up the MOSFET. Right, so this part would not be good for a logic level application where all I can do is drive the gate to source at 3.3 volts. If I could drive it at 5 volts, right, that's looking way better. So this is like probably a 5 volt sort of logic level part. So when you're looking for parts, you've got to be really careful with what the VGS drive is, because you might have a part that would work totally fine if you could drive the gate to 10 volts, which is a normal MOSFET drive level, but if you're driving it at 3.3 volts, it's not going to work. So let's switch to Digikey now and look at a little MOSFET search. Okay, so if we're back on Digikey, we could search for MOSFETs, or I'm just going to look through here, single FET MOSFET. I always just search in stock. Let's make the font a little bigger for you. Always go for in stock. We don't care about out of stock stuff. We're going to have lots of results because we're going to have a pretty vague search selection. We want N channel. And one of the first things we're going to figure out is what drain to source voltage do we need. So if this is a system working at, say, 12 volts, we want to be higher than that. If you go above this, it'll destroy the device. So I might do 24 volts, right? We may have spikes higher. So really, it doesn't hurt to go much higher. As the voltage goes up, right, the cost of the MOSFET is going to go up as well. You're going to have, for a given MOSFET, if I have a 100 volt MOSFET, it probably will have a lower current handling capacity than a 24 volt MOSFET. So we don't want to go too high, so I might go into the 24 to 100 range. For this design, this is very straightforward, so I'm not too worried about that. And then we want to look at we want to look at a few things. We want the drain current, right? So this continuous drain, we know we potentially could go up to 5 amps. Our fuse is going to kick in above that. And so I'm going to pick something above 5 amps. We're going to narrow this down quite a bit more. So let's say if I go even 10 amps. I know for sure that we're going to have a lot of choices at this range, so I'm not too worried about limiting myself too much. And the higher current limit doesn't matter that much. We're also going to get limited by package size. I don't want a huge expensive MOSFET, right? But I might go way up here to like 100 amps. And you can see in the example assignment, there's a different set. I'm kind of going off my own choices here. So if you're doing the assignment, use what's in the assignment. I'm just kind of selecting something. So we still have 5,366 MOSFETs to select from. We could filter. I won't do it yet, but you can see some of these packages are going to be more annoying to solder. So if I knew I was prototyping, I might pick, this is a pretty standard package. It's called DPAC, and we'll get into packaging in a second when we look at KiCad. SOC 8 is a really easy package to solder, right? This guy is annoying. You can see there's pads in the bottom. That's going to be super annoying to prototype, so I'm not going to do that. So we may try to filter a bit based on that. But before I do that, what I'm going to look at is the gate voltage. And here's where you can see this RDSon max. This is the maximum allowed value for that RDSon, and it's spec'd at a current and a gate voltage. So you can see a bunch of these are spec'd at 10 volts. If I'm doing a logic level driver, that 10 volts that's not something I'm going to have access to. So what you want to do down here in drive voltage is make sure you're selecting everything that mentions the lower voltage. Normally for the lower logic level, I might just select the 1.8 to 4.5 because 4.5 is then the maximum possible drive voltage. I know it's going to fully turn on below that. I'm going to select some of these ones that also mention a lower voltage, and we'll look at, so this is 2.8 to 10 volts. So at 2.8 volts, there's a higher RDSon, and it might be too high for my application. I'm suspicious because normally I would just filter everything. I'd say I just want maximum 4.5 volts, but I'm going to keep some of those in. And above this, I'm not going to go because these start getting into, and we could say 3.3 to 4.5. That's potentially useful, right? But I am driving this from 3.3 volts, so we don't want any of those 4.5 volt ones. That's a standard MOSFET drive level. We don't have that in our system. So now we've got some MOSFETs to select between. So it's only 25, so it actually cut it down a lot. I may have been too restrictive. And so I might go back and look at what did I over filter on. Is it drain to source voltage? Is it, do I want to look at out of stock stuff? I suspect it's probably this drive voltage. because if we get rid of that, we'll suddenly have the 5,300. So sometimes what you do is, I might have selected, sometimes the filtering goes in a weird order. I missed, and it does this live, so that's kind of always handy. You know, it's not this. You can see, is there one that as soon as I click it, it's giving me thousands of results. So I clearly missed one because I'm up to 43, which is pretty good. So let's just go with those. Okay. And it may be that I may actually want to go down to my current limit. I may have been way overzealous selecting 10 amps. That's super overkill for our design. But you can see here, we've got a pretty good selection of MOSFETs that are coming through. And again, I'd want something that's a little easier to prototype with. So we're still not getting that. So I'm going to drop the drain current. So again, this is kind of an iterative process. I tend to start pretty aggressive like that. In the design, I actually only need 1 amp, so I've really gone overkill because 5 amp is where it's fused at. So let's go down and let's go a little higher. Let's say like 3 amps and above. And just put all the 3 amp and above options. So now we have 163. So that's looking better. And the reason I've kind of done this is, you know, these parts are going to be much easier to prototype with. So these little packages, there's just 3 pins to solder. So that's going to be a lot nicer than these things. Not that you can't use them. I just know it's going to be more annoying to solder with. Okay, so I was hoping we'd have D-Pack or something. We don't have that, so there's a slightly bigger package that's for power MOSFETs. It's often handy. These types with the weirder packages you can often find in KiCad. What I wanted to show you is if you're just picking a random MOSFET, like say this guy here, how do you get that into KiCad? So if we take a look at the datasheet, there we go. We can see, so it's got a good drain performance. So watch out, right? This is where it can only dissipate 1 watt of power. This is where that RDSon can be a bit tricky. If you don't turn it on very quickly, if you're trying, especially if you're trying to use this for motor control where you might be using pulse width modulation, this becomes more of an issue. But the other thing with MOSFETs is do not exceed these limits at all. So the gate to source, if you exceed that temporarily even, for example, will destroy the part. And with something like an inductive load, we do have to worry about the pulse drain current here. So you know, if you're driving a motor or something, this is where you're also going to really have to overspec it. But either way, whatever we're doing, we're selecting our MOSFET. And I'm just going to see if we've got, you know, here's like so this is drain source. We want that gate voltage. So here's like the gate source voltage and the drain current. So right, it's actually, what you can see is that above, you know, 1.6 is basically turning on fully. So this may even be, you know, we may have been able to go for a higher, a better logic level MOSFET or something. That may have been my limit here. This is sort of done live, so I didn't select one ahead of time. But okay, so in here, this is the RDSon for different currents. This is interesting, right? So you can see it really drops. Like as soon as we're above 3 volts, it's like 0.015 ohms. So this is in milliohms. So we should be pretty confident that we can turn this thing on and it hopefully is very reliable for us.